So now we come to the next polysaccharide, that is of starch. And starch is the main storage polysaccharides of plant. It is the most important dietary source for human beings. Also, a high content of starch is found in a number of cereals, vegetables, and such. Now, starch here, what is the main factor that we are keen about is that the monomer of starch, which leads to the formation of this polymer. So now it is the main monomer is nothing but alpha D glucose. Now we know what is alpha D glucose. So here we have 3 units of alpha D glucose, and we will see how they will be forming the polysaccharide, that is starch. Now, if we are talking about the alpha one, the alpha D glucose, we know that the OH will both lie on the cis position, that is on the same side. So let us first draw all the OH. Now, when we are done with the OH, now we want a glycosidic linkage between these two alpha D glucose, these structures. So the glycosidic linkage that is existing here will be between our C1 and C4. So we'll be seeing a loss of OH and H, that is a water molecule, and the formation of a glycosidic linkage. So how is this glycosidic linkage formed? So we remove them and we are only left with an oxygen over here. So this will lead to the formation of an ether linkage, and this is how we form the glycosidic linkage. So it is between first, so this is second, third, fourth, and fifth respectively. Also, if you see the second one, 1, 2, 3, and this is the fourth. So a formation of glycosidic linkage between the first carbon and the fourth one of these two alpha D glucose. Also the same will happen with the next one. So we are left with a linkage, a ester linkage between them called the glycosidic linkage, that is the linkage between two monosaccharide units, and we can continue them over here also. See, over here, this is the fourth carbon and this is the first one of the last one. So you can see that the fourth is getting attached to the first, so we can just see an open structure over here. So we'll make them in such a way that we are aware that the chain continues ahead, in such a manner that there is another unit of alpha D glucose present on the side. So this particular, the straight chain structure that we have just seen is a component of starch. So starch basically is made up of two components. This is the first component that we are seeing, which is a straight chain component, and this is called amylose. So the name of this is amylose. Now, starch basically is composed of two constituents, that is amylose, which we just saw, and the second one which we will see is amylopectin. Now, what is the difference between both of them? The difference is in the glycosidic linkages that they'll show. So first let us just observe this amylose that we have just seen. So in amylose, the glycosidic linkage is between the C1 and C4. So we have C1, C4 glycosidic linkage here. So that is the main factor that we are seeing in this particular amylose. So amylose is water soluble component and it has less percentage of existence in starch, that we'll see when we talk about amylopectin, and it is a long unbranched chain with almost 200 to 1000 alpha D glucose units held by C1 C4 glycosidic linkage. So imagine 200 more units lying on the right and the left hand side of this amylose. That is how huge this amylose is, and it is one constituent of our polymer, that is starch. Now, next we see the second component that is of starch, that is amylopectin. So we're talking about now amylopectin. Now, what is the differentiating factor of amylopectin from our amylose is that lies in the glycosidic linkages. Now, Let us just see, since we saw amylose, which was a straight chain polymer, now we'll be seeing amylopectin, which is a cross-linked polymer. That means, let us just see this. Now there are two lines of monosaccharides units, a lot of monosaccharides units you are seeing here. And in the first row over here, let us just draw the amylose which we just learned. So amylose was nothing but a glycosidic linkage between the C1 and the C4, and it is extending to the rest of the structure. So we have got this structure of amylose, and if let us just draw in a second row also the amylose, and it looks something like this. So we know this is amylose because there is presence of alpha D glucose all over the place, and we can see that they are combined with glycosidic linkages existing between C1 and C4 carbon of both the amylo. Now we have drawn amylose in these two rows. Now how do we draw amylopectin? So amylopectin, here there is glycosidic linkages. Now C1 C4 glycosidic linkages you've already seen. So unit of amylose, and we have seen that the first and the fourth linkages is the highlight. So the first, the fourth, all of them, the first, the fourth, extending outwards. So we have got a lot of linkages extending outwards. Now what is happening is we'll be seeing a extension from C1 to C6. Now which one and which 6? So I will be taking the first carbon over here. So this was the first carbon, and we know that OH was existing over here. So now what is happening is, in this particular unit, call it the terminal unit. Now in this one, this unit will be losing an H and combining with, so this is lost an H, and this is combining with the sixth unit of this. So this is first, second, third, fourth, fifth, and this is the sixth carbon. Now this sixth carbon and this O will form a chain. And how do they do that? So this CH2, we lose a water molecule when a glycosidic linkage is formed. So a water molecule is lost, H from this particular O, H from this particular O, and OH from this particular CH2. Now these two combine. Can you see this combining bond now? So these two combine, and we are left with another glycosidic linkages existing between the first and the sixth carbon respectively of these two chains, and we can call them the glycosidic linkages, and the branching occurs by C1 C6 glycosidic linkages. So here in amylopectin, what we saw is that it is a branch chain polymer. So let us just write down that it is a branch chain polymer. So there is branching occurring over here. So that it is why this is known as a branch chain polymer or a cross-linked polymer. So branch chain polymer of alpha D glucose units in which chain is formed. So units where chain is formed. Now we are writing about the glycosidic linkages. So chain is formed by C1, C4 glycosidic linkages. So these lead to the straight chains, whereas now straight chains are formed by these linkages. Branching occurs. So there is branching occurring also. So branching occurs by C1, C6 glycosidic linkages. So this is an example of a cross-linked polymer. Okay, glycosidic linkages. So we just saw amylose, and now we're seeing amylopectin, and these are the two components of our starch. And amylopectin here is insoluble in water and constitutes about 80 to 85% of our starch. Now amylose was constituting the less percentage of the two, So amylose is present in less quantity, whereas amylopectin, the branch chain polymer, is existing in a greater quantity in our starch. And these two forms, one of which is a straight chain and the other is a branch chain, are the constituents of starch, which is found in plants. So this was starch, an example of polysaccharides having two components, amylose and amylopectin.